All right. Hello, everyone, and welcome. My name is Michael, and I typically talk about language design in Kotlin, and today it's not an exception. While I'll have to pretend that I'm a functional programmer, while the language itself is not really that functional, but a normal multi-paradigm programming language. And first of all, my question to you is how many people here are familiar with Kotlin? Please raise your hand. Good. So actually, most of you are familiar, but still, I'll just do a quick introduction into the basic syntax so that we are on the same page. So we start with functions, some effects, and then talk about how it works in Kotlin and other ecosystems and programming languages. So functions, they are pretty straightforward in Kotlin. We declare with the keyword fun. Here we have a function that takes a generic list of some items, do a simple for loop, and prints all the elements in the list. So pretty straightforward. And if you want to make it more abstract and not only prints, we can introduce a higher order functions. And in this example, we take two parameters. One of them is list, the other one is just a function which works from some elements of t and returns unit. And in the body of our for loop, we simply invoke this f function. And now that our previous print all function can be just like a simple use case, like a case of this more generic one where just simply invoke for each function and pass a lambda and print elements. And because it's a last argument of a call, this lambda, we have a convention that we took from Groovy so that we can use it as a dangling lambda and use a shorter syntax. And here you can see it parameter. It's an implicit parameter for the lambda. You can use it when you have just a single parameter for it. And if you want to give it a name, then you can use an explicit form and pass it with a specific name. Good. Another thing that will be needed today for us is that apart from regular functions, we have also so-called extension functions. Instead of passing a few parameters and where the main actor here is list, we in Kotlin can use extension functions. And in this case, these functions in a way it extends lists that we have now this operation on our list, and we can call it by invoking dot on our object of list. At this point, it's important that it's just a syntactical trick. It's still a proper it's a statical dispatch. We actually do not add any methods to our list. It's just a language syntactic feature, which allows us to do a slightly more preachy syntax at the call site. And because we have functions and we have functional types, now we have extension functions, and of course we can have extension functional types, which can be then more useful to bring, for instance, builders to your DSLs. For instance, here we have a function build list, which takes another function, in this case another extension function, which works on a mutable list, and again returns unit. And inside this function, we create first an empty mutable list, invoke this extension function, and return a read-only version of it. So that at the call site, we can invoke this build list. Because it's a single lambda, we can use a dangling lambda syntax without additional parentheses. And inside this lambda, because it's an extension for a mutable list, we have all methods that are declared on a mutable list, including add all, remove, whatever there are operations. And then, as a result, you can get a read-only list and then use it somewhat later. So, just to recap, again, we have functions, we have functional types, we have extensions, we have extensional functional types, and then lambda. And at this point, as it happens with lambda calculus, your possibilities are endless. And with this knowledge, we can already build any kind of type-safe DSLs for generic markup codes to draw UI. Probably you've used build Gradle KTS, which consists mostly of those functions. And for instance, here it's an example, like it's a hello world of in a Jetpack Compose library, which draws some UI. And here we have column, text, spacer, button, and all of them are just pure functions. They just, it's not like objects, they're just the functions in the create scope where you can invoke other functions and draw your UI. But again, at this point, it was mostly like a syntactical thing. Like at the runtime, they just compiled down to like regular functions. And for the today's topic, we need like a slightly more complicated thing. And we have to introduce first another kinds of functions, which are suspend ones. And suspend functions, it's our way to do concurrency in Kotlin. And at the runtime, if we take a look at this function, we can see that actually at the runtime, it takes an additional parameter in a form of a continuation. And now it returns not just a string, but a string or a marker that a specific coroutine was suspended. So if we take a look at this example where we have suspend fun foo, it prints something, then it invokes another suspend function like delay, and then prints the second string. Then at the runtime, if we simplify this thing quite a bit, it actually, again, it's actually our function foo that takes a continuation parameter. It invokes, it executes the first part before the first suspend function, and then it returns the result of our delay function that also takes the continuation that knows about the second part, which will be invoked when the delay function resumes. So it's like a typical CPS style that is very, very familiar, but just is backed at the bytecode level. And here, the important part is that here every suspend function, it actually takes an additional parameter in form of continuation, which can also already be a sign of a potential problem for the future. Because again, if we take a look at this function foo, we can invoke regular functions like println. We can invoke other suspend functions like delay. But of course, we cannot invoke suspend functions from non-suspend ones, because regular functions, they don't have this continuation parameter, and we cannot materialize it from the air. And this problem is known simply as code coloring. And there are many, many instances of this problem. And why it's called coloring is that because, of course, we marked our functions like into colors. So suspend functions have one color, regular one functions have other color. And it's typically considered like a problem because now you have to, it's complicates your refactorings. You have to, if you want to call a suspend function, you have to mark your function itself as suspend, and then call it for that function again, you have to mark a suspend or do something else. So it can be problematic. However, it also like presents in many, many languages. For instance, in Java, you could see that in form of like checked exceptions with throws. Like in Kotlin, TypeScript, Python, Swift, Rust, it's all about like async await or some sort of concurrency. It's worth to mention that in Java and Go, they managed to do this without code coloring because they kind of can introduce stackable coroutines, which where like coroutines, each coroutine has its own stack, so they can manipulate with this continuation object on a slightly different level, and they don't have to materialize it out of the air. And while it's considered problematic, I personally think that its code coloring is, of course, it's not great, but it's actually not terrible at this particular moment, because sometimes it actually makes sense to mark like suspend functions or like functions that do some concurrency stuff like in explicit form, so that I know that this particular function can suspend. And still, while it's quite tedious to mark and your functions with suspend and do refactorings, it's an important thing is that it's easy, that you just slap a suspend modifier and go further. And then you adapt your callers for these suspend functions. It's dull, it's tedious, but it's easy. And also it's important that for the compiler, it's also easier for the compiler because like we know at the compile time which functions are going to be suspended, and so that we can perform certain optimizations and build structured concurrency trees and so on and so forth. While in stackable coroutines, we know this information only at runtime, and we do not have any other option than just copy stack and do more expensive stuff at runtime. And again, at this point, it's more or less fine. We can live with that, but let's go further. And because we have functions and functional types, extension functions and extensional functional types, the story with suspend functions is the same. Like we have like suspend functions, which means that we have to have suspend functional types. And what happens at runtime? At runtime, it's again the same. Lambda, which is marked with suspend, is actually transformed into like a regular lambda, which takes, again, a continuation parameter and returns now a unit or a marker that this specific coroutine was suspended. And at this point, again, you already can see a sign of a problem, because if I have my suspend fun foo, if I have my regular fun bar, then if I invoke this bar and try to invoke a suspend function in it, I will get an error. And in this problem, of course, let's slap a suspend modifier here, like as what is in the previous case. But if I do this, the error is still there, because here we trying to invoke function foo in another function, like in its lambda, and we don't know how this like closure is going to be used later. Maybe it will be stored in some hash map. Maybe we'll do something like it so it will escape or like persist or serialized, so that it won't be possible to resume our coroutine later. And this problem, compared to the previous one, is really, really nasty one, because it's now at this point, it's way, way worse. Because here we don't have like a clear way out. We cannot mark just our function and suspend and go further. Like we have to either somehow change our bar function, so like our regular function, so that it can accept suspend lambdas, but often we cannot do this because it's a library function. And so it also means that as a library author, you have to probably duplicate your API. And it also means that I cannot simply abstract harmless pieces of code, like my pretty for each function now doesn't work with like half of my functions which are suspend. And also why it's like a actual problem compared to previous one is that because we don't have like a clear way out, people can become very creative at that point, because when they don't know what to write, they write something. And just an example that's from Java, where the problem is the same. So you probably saw that it's here we have again, we invoke just for each, we pass a lambda, and inside it we invoke a function read file, which actually just throws a checked exception. And throwing is actually another effect, like as the same as with concurrency and suspend operations. Throws is another effect, and here it's the same, because this for each and lambda can be used somewhere. The compiler emits an error and it forces you to do something with this code. Like, please, like this exception is not handled. Please do something about this. And people who just less familiar with Java, with how you should treat these things, they write the simplest thing that is possible, the shortest one, and usually the shortest thing becomes the default, and they just follow all the exceptions. Or sometimes they just do some logging and again swallow all the exceptions or part of them. And I saw like hundreds of issues in actually in our IntelliJ, which causes this problem. While in reality, the best thing that you can do is just to rethrow exceptions as an unchecked one. And you can imagine the similar thing happens with suspend or async awaits, when you cannot invoke a suspend function or your async function. And at this point, you become creative. Maybe you can just turn this piece of code into a synchronous one, so that you'll just forget about all your async stuff or do something else. That's a problem. And if you take a look at the other languages, so the problem is actually, again, all the same. Like Swift has the same async await. Rust has this problem with async, like const expressions, like error handling. And if it like the same, like if you try to write things like a typical functional map and try to do await in its closure, then you get an error because, again, the compiler doesn't know how to perform this await operation. And you can just adapt simply map to make it async one, because now you have to teach your map operation how to work in an async context. So a typical thing in Rust is to provide the second function map async that will work with suspend closures, with async closures. And because they have more effects, they try to address this with a so-called keyword generics initiative, where you can mark your functions with async question mark, const question mark, error question mark. It's like it wasn't in the development for 3 years. It's still under development, like because of reasons. And but it was a nice initiative. But unfortunately, they still didn't reach the end of it. And because we are at the functional programming conference, like my question to you, like, how is this solved in functional programming? Because like in functional programming, like when you run into like stuff like this, like you really have to think like the solution should come to your mind like immediately. So what should you do? So the first thing that as a functional programming, when you see a problem, you don't have like many options. Like you really have to, you have a problem, and you have to first turn this problem into a value and then use a type class over it. And that usually solves all of your problems, because whether it's like error handling, whether it's I/O, whether it's like concurrency, whether it's return, it should be just a value. You don't have like that many options. And then you have to do it like a more generic and introduce a new like level of interaction and use a type class over it. And it brings some uniformity, and it actually, if it works for you, then it's great. But the very major concern, like from my perspective, is that now we have this quite a complicated thing in our language, in our system. And for instance, this for each, or like this traverse, becomes quite convoluted. For instance, we have now this f, which is like a placeholder for some effect. There is a type class that so is bounded to applicative. And our previous for each functions, which used to be just a for loop, becomes quite something. And while people argue that, yeah, code coloring, it poisons your code, and then you have to mark your functions with something, this thing actually poisons your design system, like in a much harder, because now you have to follow this design and paradigm in your whole system. So, but I promised to show it how it's done in Kotlin. So let's return to our original example. So we started this for each, which is like a simple for loop. And we wanted to solve this problem that if I try to invoke a suspend function in it, then today I get an error. Interesting part here, if I change my for each to for each from the standard library function, then it actually works. And the idea is the following, that for each in the standard library, it's still like a regular for each with a for loop, and it's just like a single declaration. There are no like overloads for it. But the thing is that it's actually marked with an inline modifier. And this thing can be quite confusing, because in Scala3 you have inline, like in some other like languages you have inline, but it's slightly different in Kotlin. In Kotlin, if you have like a function like now this print all, inline in Kotlin means that you can simply inline the whole body of your function at the call site. So this list.forEach becomes a regular for loop inside your suspend function. And at this point, it's clear that we actually do not have any problems with continuations, like, because like we do not have to pass it anywhere. It's like just in line. And yeah, we can simply use this Lambda inside our code. And we preserved the simplicity of our for loop, and now but also this for each can work with regular functions and suspend ones without any problems. So the inline functions in Kotlin, they just, from the compiler perspective, they just inline the function body at the call side at every time. Like, interesting part here is that originally we added them to Kotlin just to avoid extra allocations of objects for lambdas, because it was like 15 years ago when we were designing this. And at the time, creating an object for each lambda considered expensive, and this inlining actually helps to do some runtime optimizations. And later understood that this actually can support like this way, like reify generics. We had introduced transparency for control flow effects and so on. And so that today, if you take a look at Kotlin's standard library, all like not all, but most functions like map, filter, reduce, some utility functions, they're all marked with inline in Kotlin, so that when we introduced suspend function in Kotlin, we didn't have to change like half of our library or produce overloads that they can work with suspend functions. And while it's suspend function is just one of the effects, so the other effects is just actually like a regular return or like non-local jump. It's also can be considered an effect. And again, inline functions can simply work with it, because now that if I try to write something, a function like first elements of groups, and just I have list of lists, and when I do like my map operation, if I see like this group is empty, I can simply return a null from the whole function. I don't have to introduce like a Boolean variable where I put that, oh, there's actually an empty group inside it, so that after my like map operation, I check it and return a null. That's not necessary. It's possible just to make a non-local return from the function altogether. The other thing is that it's not really related, but again, it shows that these inline functions are transparent, is that here, what I can do is that on JVM, we have this problem that we don't have reify generics. And what I can do now, but with inline functions, because it all happens at compile time, I know everything about my types, and I can write things like filter with instance, where I can just take a collection of some iterables, I go through it, and perform like a regular type check as in regular code. But in this case, it's generic. And now when I have like a list of something, I can do like a simple filter with instance of string, and it returns list of strings. So very easy. Great, but are there any trade-offs? So we are fighting code coloring, but actually in order to fight this code coloring, we introduce another colors to the language, because now that lambdas of inline functions, they are sort of executed in place. So it works because inline functions that take functional types, they cannot be stored, for instance, again, in a hash map, because it's not going to be inlined, which means that such functional types, they have now a new color. And again, it means that if you have like a functional type inside your inline function, you cannot simply pass it to a function that is not inlineable. However, in practice, it shows that it's not that often, it's not really necessary, but still it applies some limitations on your inline functions, and you can't mark like every function inline in your code, and maybe it's for better, because now it means that only some sort of simple functions can be inlined and marked as inline, and then they can naturally work with all your effects across your code. And just like a short summary, it's actually the end of my presentation. Like what I wanted to show that is like code coloring is almost everywhere. And mostly it's most often it manifests around concurrency because it introduces a new kind of functions to languages. So it's the same happens in Rust, in Python, in TypeScript, and so on. Code coloring, like for regular functions, is not that bad because again you have like a clear way out. Like you can adapt your code while it's maybe not that pretty, but it's relatively easy. But code coloring for higher order functions is much, much worse because there is no clear way out. And just when you run into such a problem, like be sure that you know how to deal with it. Like do not try catches and swallow all the exceptions or turn your piece of code into like synchronous one. Like think in advance, maybe use some sort of a linter in this case. And this problem can be solved, at least in today's world, with an additional level of indirection. Like if you're like want to use like a functional style with type classes and using like effects as values, or can be mitigated with a thing like in Kotlin, just like inline functions. And if you're considering a new programming language, then you consider also this technique and maybe use this in your language as well. And actually, that's it from my side. I finished quite early, but if you have questions, then you can discuss it. Thanks.